Hey there, welcome back to another Mate Science Easy physics lesson. In this lesson, we're going to be having a look at the concept of freefall. We are going to have a look at how it links in with speed, velocity, and acceleration. So the first thing that we're going to have to ask is, what do we mean when we say freefall? And essentially, freefall is a description of any object falling with only gravity acting upon it or only gravity pulling it down. And on Earth, gravity pulls all objects downwards at a rate of acceleration of only 9.81 meters per second squared. So anything falling within the Earth's atmosphere accelerates at a rate of 9.81 meters per second for every second that it is falling. Now, this is really important, and a lot of people get this wrong. A lot of people think that the heavier an object is, the faster that it falls. In reality, the mass of an object does not affect the pull of gravity. All objects, regardless of their mass, are pulled down by gravity at the same rate. So everything accelerates at 9.81 meters per second squared if it's being pulled down by the Earth's gravity. So we would expect two objects to fall at exactly the same rate. So if we take a feather and a bowling ball and we drop them, we find out, well, unsurprisingly, despite what I've said, that gravity pulls all objects at the same rate, we find out that the bowling ball falls faster. It appears that gravity is pulling the bowling ball faster than the feather. Now this isn't actually the case, and there's something else going on. And it's linked to this idea that freefall describes an object falling with only gravity acting on it. Something else is acting on these objects as well as gravity. So the bowling ball does fall much faster than the feather because there's something else going on. And this is because the objects are not in freefall. Another force, and that force is air resistance, is acting on the objects and it's affecting the rate of acceleration. So, air resistance is working in the opposite direction to gravity. And because the feather has a less aerodynamic shape than the bowling ball, air resistance is affecting the feather much more than the bowling ball. So it appears that gravity is affecting the bowling ball more. However, both objects are being pulled down by gravity at exactly the same rate, but because they're not in free fall, they do fall at slightly different rates. Now we can illustrate this point by looking at what might happen on the moon. So remember, free fall is described as an object falling when the only force acting upon it is gravity. So if there's no air resistance on the moon, only gravity is acting on this object. So the objects falling will be falling in free fall. So if we take our feather and our bowling ball this time and we drop them on the surface of the moon, both of these objects fall at exactly the same rate because there is no air resistance holding them up. So both objects fall at the same rate. However, they fall slower on the moon than they would do on Earth because the moon's gravity is weaker than the Earth's, so the rate of acceleration is going to be less. But this demonstrates very clearly that free fall occurs whenever only gravity is acting on an object and that all objects fall at the same rate depending on how strong gravity is. So even though a feather has far less mass than a bowling ball, if only gravity is acting on it, it will fall at exactly the same rate as the bowling ball. Now on the moon, gravity is 1.6 meters per second squared, which is slower than on Earth, so the objects fall slower. Now another concept that I want to look at, as well as free fall, is something known as terminal velocity. Now we know what velocity means. Velocity is the movement of an object in a specific direction. So it's not quite the same as speed. It is a vector, not a scalar. Terminal essentially means final. So we already know that any object falling towards the Earth is going to accelerate at the same rate as gravity. It's going to accelerate at 9.81 meters per second squared. Also, just so you're aware, sometimes we round this up to be 10 meters per second squared, and that's fine as well. Now, as the object falls faster, their speed is going to increase, and their speed will continue to increase. But as their speed increases, so does the air resistance. So we can see here, this person's falling quite quickly, and we might have air resistance of, say, 4 meters per second squared. So these two forces are going to start to cancel each other out. This person is still going to be falling, but they're going to be accelerating at a rate lower than gravity because air resistance is acting in the opposite direction. Eventually, as their speed becomes faster and faster and faster, the force of air resistance is going to be equal to the force of gravity. So you're going to have gravity pulling a person down at a rate of acceleration of 9.81 meters per second squared, and you're going to have air resistance pushing up with that exact same force. If those two forces are the same magnitude and they're acting in opposite directions, those two forces are going to cancel each other out. So when air resistance is equal to gravity, the parachutist or any object that's falling can no longer accelerate. They're now travelling at a constant speed because the downward acceleration and the upward force have cancelled each other out. So their speed can no longer increase. This is their maximum speed. And we call this speed, where air resistance is equal to and therefore cancelling out the rate of acceleration due to gravity, terminal velocity. I just want to take a little break in this lesson to tell you a little bit more about Make Science Easy, and you can visit us at makescienceeasy.com. At our website, makescienceeasy.com, we have complete science courses for biology, chemistry, and physics. These are just like this lesson, but in lots more detail, covering everything that you need to know to pass your science exams. Every course, so the biology, the chemistry, and the physics, has over 65 lessons to it. Every lesson also includes printable resources, question and answer sheets to make sure you've understood, and multiple choice quizzes that you can take online, and you get an immediate grade to see how much you've understood and if you've really learned the concepts. If you want to sign up for Make Science Easy and get access to all these lessons, there is a free trial, but at the checkout, if you want to purchase full access, you can save 50% by entering the code YT50. Okay, so we can take this concept of terminal velocity and we can extend it a little bit by seeing what happens to an object that rises up and then falls back down. So we know that gravity pulls all objects downwards with an acceleration of 9.81 meters per second squared, regardless of if they're travelling upwards or downwards. So if something's travelling upwards, it's going to be slowed down by gravity, and if something's travelling back downwards, its speed is going to be increased by gravity. But the rate of gravity is always the same. It's always 9.81 meters per second squared, pulling downwards. So if we take a tennis ball and we throw it up into the air, as it travels up, it has negative acceleration. It slows down. Its velocity becomes less because gravity is pulling down on it, slowing it down. As the ball falls back down to Earth, it has positive acceleration and its speed begins to increase again. So at the peak of this ball being thrown upwards, so at its maximum height, its speed or its velocity drops to 0 meters per second. Acceleration due to gravity then causes the ball to fall back down to Earth. It's being pulled the whole time, whether it's travelling up or down. Gravity is constantly accelerating it downwards. Now, the speed that it reaches as it lands back at its original point will be exactly the same as the speed that it started at. So if we throw the ball initially at a speed of 20 meters per second, so as the ball travels upwards, its speed will slow. It will reach a speed of 0 meters per second as it reaches the top, the peak of its height. It will then accelerate as it travels downwards to a speed of 10 meters per second at exactly the same point, height-wise, as when it reached 10 meters per second traveling upwards. And when the ball lands and reaches the same point that it started from, its velocity will be the same but in an opposite direction. So, the speed that objects travel with is changed by gravity. As an object reaches the maximum height, it reaches 0, and the speed will then increase as it accelerates due to gravity again. So we can plot these speeds in a table, and we can see that at a time of 0 seconds, the ball hasn't travelled at all, but it's just been thrown, and it has a velocity of 20 meters per second. After 2 seconds, the ball has reached a speed of 0 meters per second, and it's travelled a total of 20 meters upwards. The ball will then fall back down. After a further 2 seconds, it will land. It will have travelled a total of 40 meters, but 0 meters from its start point, and its velocity will be the same as when it started. And we can plot this information into a graph. So we write our title, we draw on our axes. Along the x-axis we have time, because time is independent. And along the y-axis we have speed in meters per second, because the speed is dependent on how long ago the ball was thrown. We then plot on our units. We make sure that every square in both the x and y-axis direction has the same value. So all of the squares on the x-axis have the same value. All of the squares on the y-axis have the same value. We can then plot our points, and we can see that our graph looks like this. We can see that as the graph is travelling upwards, so up to 2 seconds, its speed is constantly decreasing at the same rate. Remember, on a speed time graph, a straight diagonal line, if it is downwards, shows a constant rate of negative acceleration. As the ball reaches its peak at 2 seconds, it starts to fall back downwards, and it accelerates at a constant rate of 10 meters per second squared. So we see we have a straight diagonal line showing we have a constant rate of acceleration. Now we can also show the path of this ball using a distance time graph. Now when we say distance here, we do mean distance from the start. So we do what we did before. We write our title, we label on our axes, we write on the names of our axes, so distance and time. Time always goes on the x-axis because it's always going to be, at least for motion graphs, it's always going to be the independent variable. We write distance on the y-axis because it's going to be the dependent variable. We plot on our units, making sure that every square is worth the same value. And we then plot on our points. Now remember, this is a distance time graph, so a couple of things to notice. A curved line on a distance time graph shows acceleration. It doesn't tell us if it's constant or if it's variable, but it does show us the rate of acceleration. And we can see that the curve is flattening as the ball travels up, so it is showing negative deceleration. And the curve is getting steeper as it travels back down, so it's showing positive acceleration. You'll also notice that as you get to 2 seconds, as you get to the top of the curve, the ball has stopped moving. Its velocity for a very short amount of time becomes 0. Now we can show a third graph for this, and this time we can show a speed time graph for the downwards velocity of the ball. So only for the downwards velocity. We can see here our table has changed ever so slightly. So we now have downwards velocity. So we start off with a negative velocity because the ball is traveling upwards, and we end up with a positive velocity as the ball travels downwards. And we're also measuring this from the distance from the start. And we can also include time. So we plot on our axes. Here, the graph is going to be slightly different, but we still have speed and time. We make sure that every square has the same value, and we plot on our points. We can see that at 2 seconds, the velocity downwards towards the ground is at 0 meters per second. So we can see here very clearly that the whole time the downwards velocity is increasing, and the downwards velocity is always increasing because gravity is always pulling the object downwards. So any graph where gravity is acting on an object, the downwards velocity is always going to increase because gravity always acts in a downwards direction. And there's one last graph that I want to show you, and this is going to be the distance time graph for the downwards movement of the tennis ball. So again, we plot on our points, we have time and we have distance. We plot on our units, we make sure that each square has an equal value, and we then plot our graph. Now we can see again that downwards movement is constantly increasing because the ball is being pulled downwards at all times by gravity. But we can see that at 2 seconds, where the ball reaches its height, it reaches its peak, there is no movement in any direction because the ball has stopped moving. It is stationary at a very brief period of time before being pulled back downwards. So all of these graphs show the movement of the ball that we had that was thrown up and then was pulled back down by gravity. But they represent that movement in a slightly different way, and that allows us to work out how the ball is moving in more detail. And any object that is thrown up and then falls back down to Earth, assuming that air resistance is not a major factor on it, will show a similar pattern and a similar trend to these. In summary, freefall describes an object falling with only acceleration due to gravity acting on it. Near to the Earth, acceleration due to gravity is 9.81 meters per second squared. All objects should fall at the same rate as gravity is constant. Gravity on Earth doesn't change, so all objects are pulled at the same rate. However, in the atmosphere, objects do not experience free fall because of air resistance that acts on them and acts in the opposite direction to gravity. So, when air resistance and acceleration due to gravity are equal, there is no change in speed. This is known as terminal velocity. And objects are thrown in an arc are at its highest speed at the start and the end of the arc. And at the top of the arc, before they fall back down, their velocity falls to 0. And we can represent this with lots of different types of graph. So I hope you now know a little bit more about how an object falls and what free fall is and what terminal velocity is and how we can represent a falling object with graphs. Until next lesson, keep on learning.